Okay, number 4. So let E be the identity element and prove that when you mod out by that, or when you quotient by just that subgroup containing just the identity, that you stay isomorphic to yourself. Okay, so let's prove that that's the case. So there's kind of two ways to go about proving that. One way is like this, where you sort of start inspecting what the actual cosets look like. So like so hang on. So let's go with this. Let's call that K just because it'll be easier to look at. Well then, and let's say G is an element of G. One good question is what is what does a coset of that subgroup look like? So what does KG? Well, KG would be something like well, it would be just that. And so it would literally just be that. Right? Because the coset only has one element. So or the K only has one element. So yeah, so that's all there's to it. So things in here are things like KG, or in other words, just G. Whereas things in here are just the elements themselves, like just G. So you might wonder, is there a function that you could define which would give an isomorphism between those two groups, which maybe map back and forth between these two kinds of elements? And sure, indeed, there is. It's just the one that removes the set brackets, right? Because like over in the quotient group, you'd have stuff like KH times KG is K of HG, or in other words, just H and just the set G would be just the set HG. Now compare that to so this is in G mod K, or G mod just E. So yeah, whereas in G, it's like this, right? H times G is just H times G. So it's the same exact situation. It's just literally do you have brackets around your symbols or not, right? So of course they're isomorphic. Of course they're isomorphic. It's just the way you're writing it down. So all you need to do then is basically come up with a function that switches between the ways that you write them down. So let's come up with this function here. So it'll go from here to here. And here's how we'll define it. We'll say we'll take in a set like this. Right? That's what an element of G mod the identity subgroup looks like. And we're going to turn it into just that. So we're just going to remove the set brackets is literally all we're doing. And yeah, so if you want, you can go through the motions and prove that that is an isomorphism, right? So of course it's a bijection because it's, well, actually I was about to say it's the identity function, but no, it's not. But you can work through it this way, that is a bijection and that it's a homomorphism and all that stuff. So sure enough, it's an isomorphism. Okay, but anyway, that's kind of the lame way to do it, to be honest with you. The cool way to do it is to use the fundamental homomorphism theorem from the previous question. So the fundamental homomorphism theorem says that G mod K is isomorphic to H if you've got a function, if you've got a homomorphism from G to H with kernel K, right? So all we need to do, if we want this situation, then we need to find a function. If I just follow the pattern here, needs to go from G to G, and the kernel needs to be just that. And perhaps to be a little more clear, I should say the kernel of phi needs to equal that. Right? So can you think of a function which has those properties? A function which starts from G, goes to G, and the kernel is just the identity. One function should hopefully come to mind, the identity function. Right? What if you literally just take the identity function on G, right? So let's get rid of that stuff and say let phi from G, don't know where that came from. Touching the keyboard here, my mistake. Okay, did it again. There we go. All right, so yeah, so let phi from G to G be the identity. And I would say function, but really we should just emphasize here that it's a homomorphism. And of course it's a homomorphism, the identity function. Hopefully you believe me. Yeah, so then what's the kernel? Well, of course it's only E, because everybody gets sent to themselves, so the only person that gets sent to E is E. And then that's it, because now we're good to go for the fundamental homomorphism theorem. That's it. I mean, G mod, the kernel of phi, is isomorphic to the image of phi. So that's that, right? So yeah, so the fundamental homomorphism theorem, if you use it this way, can really tell the answer here, which is just that when you mod out by the trivial group, you haven't really changed anything, right? It's kind of like dividing by 1. You don't, you can, but you don't actually do anything. So yeah, okay, so yeah, so that's number 4. See you on the next one.